Welcome to everybody. I am Enrico Scala from the Dipartimento di Informatica Università di Torino. I am going to present this work about plan repair by exploiting numeric macro actions for resource-constrained tasks. I will introduce the problem of reference and some motivation for this problem, after which I will introduce the notion of a numeric macro action, and I will explain how to exploit these macro actions for plan repair. I will conclude my presentation by reporting some experiments, conclusions, and future works. Agents controlling real-world systems, such as robotic systems, are often requested to act in environments which are high dynamic. This means that at each step of the plan execution, the observations that you acquire during the execution could be very different with respect to the expectations that are provided at planning time. This is because there could be external agents modifying the world, there could be unforeseen exogenous events, and even the effects prediction could be inaccurate. Moreover, there could be also goals that can change over the time. For instance, you can have new user requests, or that can add new goals to be reached, or remove goals that are set in the first planning phase. And for this reason, the plan can become invalid due to not applicable actions, for instance, because of some missing causal link, or you can have unreachable goals. This is because new goals that have been set. And so, in order to provide the agent with a reasonable level of autonomy, it is desirable to monitor the execution of the system and to repair the plan whenever some inconsistency is detected. Moreover, this plan repair task must be done efficiently so that the reasoning that is done is still useful for the next acting. There are actually other approaches to this problem, like conditional, conformant, or probabilistic planning that try to anticipate the possible contingency at planning time, but in this talk we will focus on plan repair, and in particular we will focus on three main objectives that are pursued by this work. On one hand, we would like to handle domains that involve resources constraints, or also other numeric constraints, such as costs, quality indexes. We would like to preserve the stability of the plan being repaired, and we would like to see if it is possible to act in a planar-independent way. In order to meet the first requirement, we allow the exploitation of action preconditions and goal conditions that involve not only causal conditions, but also numeric constraints. In order to meet the second requirement, we prefer plans which are closer to the broken plan, and for acting in a planar-independent way, we adopted a problem reformulation approach. From a formal point of view, our problem can be defined in terms of the plan that must be repaired, the current observed status of the system. We assume that we have a full observability of the domain, a set of numeric actions for that domains, and a set of conditions that could be different with respect to the condition at planning time over F and X, which are the propositions and the numeric fluence of interest. A solution for our problem is a sequential plan that brings the agent from the current observed status of the system towards a status in which the goal is satisfied. And we consider optimal a solution which minimizes the distance from the previous plan according to the distance formula presented by Fox et al., which basically say that given two plans, the distance between these two plans is equal to the sum of the actions that are in the previous plan, but not in the current one, plus the number of the actions that are in the new plan, but not in the previous one. As I told you, we allow the exploitation of numeric comparison and numeric operations. Numeric comparison are basically inequalities between arithmetical expression of numeric fluence, and they can be expressed both at level of action preconditions and the goal conditions. And we could have also numeric operations in the action effect, for instance, to express consumption of resources. The main idea of this work comes from a very, very simple question, which is why is the previous plan still useful? And to this very simple question, we provide a very simple answer. That is, because it still contains solutions that are still useful for the current problem. And as a difference with respect to other work in this topic, our idea is to encode this sub-solution as macro actions in order to enrich the domain theory, together with the primitive, the original action definitions. Let me show you which is a numeric macro action. Basically, a numeric macro action is a compressed sequence of actions where its precondition set represents the sufficient and necessary condition for executing that action, while the effects set represent the implication, the cumulative implication of executing that action in the order defined by the sequence. What is new with respect to classical macro action is that we have to handle numeric fluence, we have to handle numeric conditions, and we have to handle numeric operators in the model of the action. So we defined a new construction method to build macro actions that basically inherit the basic step of the classical macro action construction, and in particular on the way two actions can be combined each other. And this method is basically based on two steps. We have a regression step and a progression step, as for the classical setting. We have other two steps, one for the classical fragment of the planning problem and the other one for the numerical one. The classical one is the same, adopted by other work in this topic, while the numerical one requires a particular attention. The problem is that when we have to deal with expression, we could have interactions between the expression that are involved in the precondition of the actions and the operator that are involved in the action that is executed before the action. For instance, if I have to execute B after A, I have to take care of what are the implications of executing A before B. In order to express this kind of interactions, we extended the regression and the progression mechanism by considering two different cases. For the regression mechanism, basically we have to differentiate between comparisons which are influenced by the execution of the action A for the combination of these two actions. And whenever the comparison is not influenced, we have simply to copy the precondition of the action B in the precondition set of the macro action. And when the comparison of B is influenced by the action A, we perform a substitution mechanism which basically perform an iteration over all the operator of A, of the action A that impact the precondition of the action B. And for all of these operators, we perform a substitution which basically store the way the fluent is modified by the action A. And so we will have a new comparison which basically keep trace of the contribution of the action A. In a very similar way, we perform the progression mechanism by differentiating two cases. When we have an independent operator, we have simply to propagate the operator effects in the effects of the macro action. When instead we have to deal with dependent operator, for instance, when the operation of the action B depends on the way the expression expressed in that operator is modified by A, we perform a similar substitution mechanism which basically newly keep trace of the way each numeric fluent is influenced by the execution of the action A. We have a very simple example from the Zenotravel domain that, of course, need this kind of mechanism in order to keep trace of the contribution, of the numeric contribution of the action. As you can see, the fly action has requirements on the fuel at disposal, which depends on the amount of fuel consumed by the action, and so the fuel must be greater than its consumption. And by performing this substitution mechanism, basically we substitute the fuel with the actual capacity of the airplane, so that in the resulting macro action, this regression mechanism will say that actually the applicability of this macro action depends just on the availability of the fuel that the airplane, the capacity of the airplane. And in a very similar way, also the progression mechanism will consider a new assignment of the fuel given by the capacity of the airplane and its consumption. So we have a compact form for representing action. Of course, if we want to construct macro that are sequence of actions, macro for sequence of action, we have to repeat this step as many times as the number of the actions that the sequence consists of. We have implemented a very simple continual planning system where we basically execute the plan as long as the plan is still valid, and whenever this is not valid, we perform this plan repair process that basically is anticipated by a macro actions compilation method that basically perform a reformulation of the plan repair problem in terms of a deterministic planning problem, a numerical deterministic planning problem, where the domain theory is augmented with actions coming from the previous formulation of the plan. But of course, we could have problem because given a plan of n actions, we have a quadratic number of contiguous action to consider, and this could become an issue from the point of view of the branching factor of the planner, and also we could have memory problems because when you build macro actions, the number of precondition, condition, and post-condition increase. And when you have to deal with long macro action, you could have memory problems. And for this reason, we implemented two methods aimed at selecting only helpful macro action. And there is a suffix prefix macro action method and a causal link macro action method. The first method basically comes from the idea to select only macros that correspond to prefixes or suffixes of the plan. It's a very simple method. Basically, prefixes, we expect that prefixes macros are closer to the current status, while suffixes are closer to the goal condition. But also in this case, we could have several macro actions. And for this reason, we basically have implemented the prune methods that basically measure the efforts of satisfying the action precondition and its contribution in satisfying the goal condition. The other strategy is based on the idea of reasoning on the actual inconsistencies throughout the plan. And in such a way that we expect that the effort of the planner is on bridging the gaps all along the plan. And the approach basically is to split the number in a number of segments where each splitting point is computed by reasoning on the upper precondition of an action and on its on the fact that it could delete some goals in the goal condition. So this is an example of a 9 action, and as you can see, for each missing services coming from the new status of the system, we have this splitting point, and so we have a number of macro capturing each segment of the plan. On the one hand, the suffix prefix macro action strategy is tend to produce very similar macro actions because the pruning technique does not depend on the previous macro action selected. But of course, we could have longer macro action, and this could be useful for having a long shortcut in the search space. The causal link macro action, on the other hand, produces smaller macros, but more representative ones, in that it is able to capture each segment of the plan. We performed experiments on 6 different numeric domains by exploiting the metric FF planning system as off-the-shelf planner, and we compared the performance with the LPG adapt system, which is the state-of-the-art in the context of plan repair, and it is the only one that is capable of dealing with numeric condition. And we use also metric FF without macro action. Cases are generated by modifying the goal conditions and the initial status of the problem in such a way to mimic a possible discrepancy with respect to the expectation provided at planning time. And we allotted a maximum CPU time of 100 seconds in order to mimic an online context. Here, the experiments, as you can see, we measured the time with respect to the International Planning Competition metric. We measured the time, the distance, and the coverage score. And as you can see, the causal link, the adoption of this macro action is beneficial in terms of time, distance, and coverage with respect to the metric FF planning system. But of course, it's not competitive with the LPG adapted system in its speedy version, in particular in reference with the distance and the coverage. But it is still competitive in terms of time, and it was a little bit unexpected. We have also other experiments, but I can show you these experiments offline. You can find something on the paper. As a related work, basically, we, as innovation with respect to the state of the art, we provided a new, an extension of the macro action in terms that we allow the exploitation of this macro action in a continual planning system. And we are able to deal with numeric condition. And with respect to the context of plan repair, the innovation apported is that is this new way of seeing the plan repair problem that is also capable of dealing with numeric condition, which is not very much common in other plan repair system, which basically approaches the problem by exploiting the partial order planning paradigm. As conclusion, basically in this work we have presented the method to deal with planning in dynamic environments via plan repair, and we have approached the problem in a planar independent way. We have seen that macro action can be extended to manage also numeric fluence and numeric condition. And this sort of knowledge is beneficial in terms of both CPU repair time and in the stability of the produced plan. We could have a lot of future works by starting on this contribution, because we can exploit numeric macro actions for offline system, for instance, a learning-based method. We can investigate, of course, new methods for the extraction of numeric action from the plan. These two methods are quite simple, but they are working. And we can study the method of the merit of these methods on other planning systems to see how this mechanism could work. That's all.
Is there any principle to formulate a macro action? And do you have ever considered the partially ordered plan as an input for?
No, actually no. It could be a good point. Yeah, but basically we extract a macro as fast as possible, because if we need to reason also on some grounding representation, we do not have anymore the benefit of plan repair. And you must be fast in order to extract that macro action. Yes, because also the planner after will reground all the action, and so yes.